First, we need to see how this has been engineered in the first place. Introducing you to the rocket equation. By the end of this video, you'll not only understand this wondrous equation that enables space exploration, but you'll better appreciate the considerations that scientists all around the world take when building rockets. Imagine you have a rocket floating in space. According to Newton's third law of motion, for every action, there's an equal and opposite reaction. So basically, to get the rocket moving, you need something to push against. Only problem is, space is basically nothing. There isn't even air to push against. So, to move, the rocket engine expels mass in the form of exhaust at a high speed. In the case of a rocket, the action is the expulsion of gas, and the reaction is the rocket moving in the opposite direction. It's just like a balloon. When air gets released, the balloon ends up flying all over the place, always opposite to the direction in which the air gets expelled. Now here's when the rocket equation comes into play. Say you have a rocket of mass m, expelling an infinitely small amount of fuel of mass dm for each unit of time, at a speed ve, which is the exhaust speed. The rocket then starts to move in the opposite direction with an increase in speed of dv for each unit of time. We can use the principle of conservation of momentum, which states that the momentum of a closed system is conserved if no external force acts on it. Considering this as a closed system, we get negative dm times ve plus dv times m equals 0, since the rocket and the fuel expelled are moving in opposite directions. Then we get dm times ve equals dv times m. Rearranging the equation and doing some quick integration, we get the rocket equation. To find the change in velocity of the rocket, all we need is the initial mass of the rocket with the fuel, the final mass of the rocket without fuel, and the exhaust speed of the fuel. This equation illustrates a critical concept in rocket science, the importance of the ratio of fuel mass to rocket mass. The more mass the rocket can expel in the form of exhaust gases compared to its initial mass, the higher the final velocity it can achieve. Now that we've understood this equation, let's try applying it using the classic baking soda and vinegar rocket. Step 1 is finding the initial mass of the filled bottle. Step 2 is finding the mass of the empty bottle. Step 3 is the exhaust velocity of the fuel, essentially how fast the fuel leaves the nozzle. For baking soda and vinegar, it's about 0.015 kilometers per second. Now, let's put it all together. Substituting our values into the equation, we get that the change in velocity of the bottle rocket is about 70 meters per second. Now, it's time to test the hypothesis. Okay, so yes, it was pretty anticlimactic. But that is partly because of the exhaust velocity. Usually, for most rockets, they have exhaust velocities of around 2 kilometers per second. Remember, for a baking soda rocket, it's only about 0.015 kilometers per second. The second reason is probably because the nozzle was too big, so all the liquid ended up expelling out at too slow of an exhaust velocity. The rocket equation is the foundation of rocket science, explaining how rockets generate the incredible speeds needed to escape Earth's gravity and explore the vastness of space. It's a great way to understand just some of the considerations engineers and scientists need to take into account. Even in a simple baking soda rocket, we can see just how many variables need to be considered and the ways in which things can go wrong. So let us not forget the incredible advancements we have made in space exploration that enables us to explore new frontiers.